Hi everyone. In today's lesson, we're going to talk about a concept called end behavior. So a polynomial function is a function made up of many terms using positive integer exponents. The degree of a polynomial is the highest exponent of any function, and the leading coefficient of a polynomial is the coefficient of the variable with the highest exponent or degree. So let's just talk about what I mean with that. So here's an example. We have a function f of x, and I want you to find the degree and the leading coefficient. So we said the degree is the highest exponent. So it looks like the exponents here go from highest exponent to lowest, and then the constant. So this example is in standard form. So we could easily look at the first one, and we could say the degree is the highest exponent, which is 3. And the leading coefficient, we said, is the coefficient in front of the variable with the highest degree. So in this case, my leading coefficient is going to be the 4, the number in front of that highest degree. So let's look at example number 2. We're looking for the degree or the highest exponent. Well, in this case, it looks like the highest exponent is actually not first. This is the highest exponent. So I'm going to actually put this one in standard form first. So standard form means we use the highest exponent first. So negative 9x to the 5th is going to come first, then the negative 4x squared, then the x, then the 7. So now we can compare the degree. Degree is the highest exponent, which I've moved to the front now, which is 5. And my leading coefficient is the number in front of that highest degree. So the leading coefficient here would be negative 9. So be very careful not to just pick the first term because it might be hidden that the highest degree is inside the polynomial somewhere. So standard form is always something that you want to do first. So end behavior. End behavior of a polynomial mirrors the end behavior of basic quadratic and cubic functions. So if you were to graph y equals x squared, some of you might even know this one, an x squared function is a happy parabola that usually goes through the vertex of 0, 0, right? Then y equals x squared is actually a sad parabola going through the vertex at 0, 0. An x to the third function you might not know specifically, but an x to the third function is called a cubic function. And what it does is the vertex is still at the origin, and it's kind of like half of a happy parabola on one side, and then half of a sad parabola on the other to get this curvy-like shape. That's a cubic function. An x to the negative x to the third function is still going to do the same thing. Still, it's going to go through our origin as my vertex, but this time it's going to be reversed. So still half of a happy and still half of a sad. It's just going in the other direction. So these 4 pictures are going to be something that you're going to have to memorize in order to be successful with end behavior. So what I'd like to show you is examples of polynomial functions that have the same end behavior. So if you look at this one, this is a polynomial equation that has a degree of 4. The highest degree is 4, and a leading coefficient of 1, or a positive 1. So it's an even degree, 4, and a positive leading coefficient, 1. So it doesn't look exactly like this x squared graph, but you can notice that the ends, the way it ends here and the way it ends here, they go in the same direction. What makes the difference between an x squared and this polynomial is that there might be some like bumps in between, and it's not going to be so straight and fluid. But the ends is all I care about, that it's ending in the same direction. So let's look at an even degree with a negative leading coefficient. So even degree, negative. So here, 4 is even, and the leading coefficient is a negative 1. So look what happens. It ends the same way as a negative x squared graph. An x squared graph ends down, down, and this one ends down, down. The only difference is there's, like I said, there's more like bumps in between. Okay? So if we have a cubic function, it's an x to the third. So if we have a polynomial that's an odd degree, like this 3 is odd, and a positive leading coefficient like this, +1. We have an odd degree here, positive leading coefficient. Look at the way that the graph ends. It ends in the same direction, up on the right and down on the left. But the difference is that there's some bumps in between, making this a polynomial function. Now, if we have an odd degree and a negative leading coefficient. So look, we have an odd degree here, negative leading coefficient in front. So odd degree is 5, leading coefficient is -1. They're going to end in the same way, up and to the left and down and to the right. But again, the difference between a regular cubic function and a polynomial is that they have these bumps in between, but they're still going to end the exact same way. All right, so let's look at some examples now. So example number 1 says, describe the end behavior for each function. So we have to combine the two things that we learned in the front page in order to answer this. So we need to know the degree. So the degree is the highest exponent, which is 5, and your leading coefficient is the number in front. So degree is 5, and my LC, or my leading coefficient, is 3. Now, all that we care about is our degree is even or odd. So since 5 is an odd number, we say that the degree is odd. And for leading coefficient, we care that it's positive or negative. So since we have a +3, we can say that the leading coefficient is positive. So because we have an odd positive, our end behavior is going to mirror the graph of y equals x to the third, because that's an odd degree with a positive leading coefficient. So that graph, if we remember from the first page, looks something like this. So we don't know exactly what this graph is going to look like. It's not going to look exactly like this, but we know that it's going to end in the same way. So there might be some bumps in between, but the end behavior is still the same. So if you want to draw a sketch of what this graph should really look like, let's just draw the ends in. So the end will be here, and the end would be here. And you don't have to draw the rest of this, but we don't know, like the graph could go up and then down and then up and then down and then connect. But all that I care about is the way that the graph ends. So the way that we describe the end behavior is we write it in two parts. So we write it as x approaches infinity. We want to know what is happening to f of x. And as x approaches negative infinity, what is happening to f of x. So the arrow is approaching. So you're going to hear that I say that. As x approaches infinity, f of x does what? And as x approaches negative infinity, f of x does what? So let's talk about positive infinity. So as the values for x get bigger and bigger and bigger, the graph is going to the right and it's getting to get closer to positive infinity. So as the x values go to infinity, the y values, or your f of x values, are going to positive infinity because this is going up. Now, when x is going to negative infinity, so when x gets smaller and smaller and smaller and smaller, where are the y values, or your f of x values, going? They're going down to negative infinity. So we could say the f of x, or the y values, approach negative infinity. And this is your description of your end behavior. I know that might have been a little confusing, so we'll do another one and hopefully it'll help. So let's look at example number 2. We're going to find the degree and the leading coefficient. So the degree is the highest power. So it looks like my highest power is not the first one this time, but it's the second one. So my highest power is 3, and my leading coefficient is -6. So my degree, my highest power is 3, and my leading coefficient is -6. So my degree is still odd because 3 is an odd number, but this time my leading coefficient is negative because of the -6. So we know that this polynomial is going to mirror the behavior of negative x to the third. So that graph looks something like this. So if we wanted to draw a sketch of what the polynomial is going to look like, we know that it's going to end in the same way. So it's going to end in this direction and this direction. So it's going to end here and here. And again, we don't know what it looks like when it connects, but it may do this, it may do this, it may do this, but the end behavior is still going to mirror this here and here. So when we're writing and describing our end behavior, we are writing it in two parts. We say as x approaches infinity, what happens to f of x? And then as x approaches negative infinity, what happens to f of x? So as x goes to infinity, or gets bigger and bigger and bigger on the right? So my infinity is here. The y values are going down. So that would say negative infinity. So as x goes to infinity to the right, the graph goes down. And as x goes to negative infinity, so as x goes to the left, the graph goes up. So negative infinity, and the graph is going up. So if the graph goes up, we say that that goes to positive infinity. All right, so I'm going to get you started on the last two, and then I think I'd like for you to finish it for homework. So the first one, we need the degree and the leading coefficient. So remember, the degree is the highest power. So my highest power here is 4. My leading coefficient is 4. So degree is even because 4 is an even number, and the leading coefficient is positive because 4 is positive. So we know that it's going to mirror behavior of y equals positive x squared, which looks like this. And the second one, we have a degree with my highest power of 8 and my leading coefficient of negative 1. So my degree is my highest power, which is 8, and my leading coefficient is negative 1. So my degree is even, and my leading coefficient this time is negative. So that must mean it's going to mirror y equals negative x squared behavior. So it's going to look like this. So take a minute, pause the video, try these problems, and then hit resume when you're ready for the answer. Okay, so for the first one, we know end behavior as x approaches infinity, f of x approaches what? And as x approaches negative infinity, f of x approaches what? So as the graph goes all the way to the right to infinity, the graph is going up. So we say f of x goes up. As the graph goes to the left, the graph goes up. So we could say the graph also goes up, and that's the end behavior. Same thing over here. As x approaches infinity, we want to know where f of x is going. And as x approaches negative infinity, we want to see where f of x is going. So as x goes to positive infinity, the graph goes down to negative infinity. As the graph goes to the left, or negative infinity, the graph also goes down to negative infinity. So that's an example of one of each. Don't stress if you're having trouble. We'll definitely go over this in class tomorrow. Have a great night.